Greetings, GMAT enthusiasts. Greetings. Hope you're doing all right. Welcome to Probability Made Easy, a partnership that Kaplan and GMAT Club are holding together. If you can see me and hear me okay, please give a hi or a hello or a hi there, a bonsoir, I guess, if you're feeling fancy, down in the comments. Make sure everybody's got their audio and video working for our festivities that we're going to have here in this 1 hour. I'm Suhir. I've been a Kaplan teacher for about a decade, demystifying certain GMAT topics. It is my distinct honor and overwhelming pleasure to be here with you, invited by the great folks over at GMAT Club. What we do at Kaplan is we take some concepts that show up frequently on the GMAT and sometimes might flummox certain students, and we try to unpack them, get them down to the nuts and bolts, and make them certainly more palatable as you move forward and forward throughout your GMAT training. So what we're going to be doing here with this session is we're going to be doing that with probability, hence the name of the session. Hence the name of the session is Probability That Is Made Easy. So I hope y'all can see me and hear me okay, and let's start getting into all of the fun stuff. So there's essentially three things that we're going to expand upon them. There are essentially three things that we are going to be in this session that we are going to be breaking down. We're going to start with some basics with the regular old probability formula. Then we're going to have not just one event, but we're going to have multiple events that are going to be going on. We'll have to make the decision, do we want one thing and another to happen, or one thing or another to happen? There'll also be the distinction between what's called dependent versus independent probability, sometimes called conditional versus unconditional probability. And there are going to be certain occasions when there'll be less work for you to do, less daylight between you and the GMAT points to figure out what's not desired and then subtract then from the total. So let's start out with just the basic formula. Probability equals desired outcomes out of total outcomes. And you can even deal with them separately, desired separately and total separately. To bring up a few kind of basic examples at the very beginning here, imagine that you had a regular die, a fair six-sided die, not a trick die, not a magician's die, just a regular die. We want the probability of rolling a 3. Now, if you picture a die, there are 6 outcomes, 6 things that die could potentially land on. What we desire is rolling a 3. So there's one thing out of those 6 that would be desired. Probability of rolling a 3 then is 1/6. So what about the probability of rolling something that's not a 3? Well, still 6 outcomes. Something that's not a 3, there would be 5 of those, 5 out of 6. But here's another way to think of it. The sum of probabilities for mutually exclusive outcomes for a given event would be 1. So if the probability of getting a 3 is 1/6, then the probability of not getting a 3 would be 1 minus that, 1 minus 1/6, or 5/6. And how about the probability of rolling an even number? Well, out of those 6 outcomes, 3 of them are even, yes, 2, 4, and 6. So our probability then of rolling an even would be those 3 out of 6, reduced, of course, to 1/2. If you like percentages better, could think of it as a probability of 50%. So we wanted to kind of start out here with some basics before we start throwing in some, kind of twists and turns than GMAT style. So let's give you a chance then to try one of these problems out on your own. Here, this question here, it's a word problem that deals with probability. You might want to draw the little picture. And if you don't recall your formula for area of a circle is pi r squared. That might come in handy for this problem. I'm going to turn my camera off and give you roughly about 2 minutes to try out this problem. Remember, probability, desired outcomes out of total outcomes, and then we're going to review. Good luck. All right, so it looks like we're starting to get some answers coming here. Looks like 125th, answer choice B seems kind of popular. Daniel Shanawaz. Answer choice B, it is. More importantly, let's talk about how we get there. You might have wanted to draw the picture here. It doesn't have to be pristine, doesn't have to be a work of art, just legible enough to be helpful to you. A dartboard with a circular red bullseye that we have in the middle. We have that radius of the bullseye is 2. The radius of the entire dartboard is 10. Probability is desired out of the total. We desire getting the bullseye. So the area of the bullseye will be our desired. And you're going to hit the dartboard, so the area of the dartboard will be our total outcomes. Area of a circle, you'll recall, is pi times the radius squared. When it comes to the bullseye, that would be pi times 2 squared. When it comes to the whole dartboard, that would be pi times 10 squared. In other words, 4 pi over 100 pi. The pi's then cancel out immediately afterwards. We have 4 over 100, and that's 1 over 25, as quite a few of you said down in the comments below. Option B, right side, right chemo. Now, here we want to kind of ease you in with probability. With this problem, there was really just one event going on. And so if you missed it or you had trouble with it, that's okay. The best way anyway to improve your performance in GMAT world is always to get burned on things and then learn from your mistakes. But let's take our relationship with probability to the next level. Because oftentimes in GMAT Quant, when you're faced with a probability question, it's not only going to be one event going on, there may be multiple events going on. And that's when there are a couple of decisions that you as a GMAT champion in training have to start making. One important decision is it an and problem versus an or problem, even if the GMAT doesn't use those exact words. Well, let me elaborate on this. If we have multiple events going on, and we desire the probability of one event and another both happen, we find their probabilities separately, and then we multiply them. Suppose we want the probability of getting heads on the first and second tosses of a fair coin. Now, for any given coin, there's heads and tails. The probability of getting heads on the first coin would be 1/2. Probability of getting heads on the second coin would be 1/2. So if we want the probability of one event and another to happen, we find them separately, and then we multiply them. 1/2 times 1/2, or 1/4. But this is when we desire the probability of one event and another to both happen. What if what we actually want is the probability of one event or another to happen? Well, then you find them separately, and then you add them. For mutually exclusive events, that's all you would have to do. Probability of A happening plus probability of B happening. If they are mutually exclusive, then they can't both happen anyway. What's the probability of rolling either a 1 or a 2 with a fair die? Well, the probability of rolling a 1 is 1 out of 6. Probability of rolling a 2 is 1 over 6. We want one or the other to happen. You couldn't roll both at the same time anyway. I think that would violate some law of physics anyway. And that would be 2/6 or 1/3. Another way to visualize it, of course, is out of the 6 outcomes, there are 2 of them that's a 1 or a 2. 1 is one of those, and 2 then is the other. But here's a little twist, a little caveat. Because what if the events are not mutually exclusive? What if you also have something that you could have some overlap? Well, then we have an extra little piece that we have to add at the end. Subtract the probability of A and B both happening. Well, let me bring up an example so it's not just theoretical pie in the sky gobbledygook. What's the probability of rolling either an even number or a number less than 4 with a fair die? Probability of getting an even plus the probability of getting something less than 4. But isn't there something on that die that would be both even and less than 4? There's a 2 on that die. That would be both even and less than 4. So if we include that, we would have double counted that event. So that's why we need to subtract it from our count ones, minus the probability of getting an even and something less than 4. In other words, probability of getting a 2. So probability of getting an even here, 3 out of the 6 outcomes. Probability of something less than 4, that's 1, 2, or 3 outcomes. But now we have to subtract the 1/6 of the outcomes that we would have double counted before, getting a 2. This is 5/6. 3, 6 plus 3, 6 minus 1, 6 gives us 5, 6. So if the events are not mutually exclusive, you do have that extra little piece that you've got to deal with at the end. So one of the big decisions to make when you're dealing with multiple events, we'll talk about the other decision to make shortly, but one of the big decisions to make is, do we have an and problem or do we have an or problem? Keep this in mind. Here's this next question up that we have on the docket for you. I'm going to turn off my camera and microphone, give you 90 seconds or so to try your hand at this problem and see how you fare. Rock and roll, then we'll review. Starting to see some responses coming up here in the comments. Looks like we got C, 5/18 coming up a couple of times, 1/12 A, 1/3. So we're starting to get a variety down below in the comments, right? This one, a slightly more challenging problem than what we had earlier with that bullseye and we had with the dartboard. So I'll end the suspense. The right answer here is answer choice C, 5/18. Now, more importantly, let's talk about how we get there. And so if you had a hard time with this one, right, you're about to get a good chance to retrace your steps, stage a little intervention with yourself, see where your mistake was. You get them next time, right? We always seek progress, not perfection, in your march towards the GMAT. We've got to consider what's desired. You're going to have two rolls of the die. We want to roll exactly one of them to be a 3. Now, consider the different ways that this can play out that would be desired. One way it could play out would be getting a 3 on the first roll and not on the second. The other way it could play out is getting a non-3 on the first roll and getting what you desire, getting a 3 on the second. If you didn't consider that those are the two different ways that this can play out to give you what is desired, I hope you already got one or two good takeaways here to take away. Now, remember the word and indicates multiplication. So for that first scenario, a 3 on the first roll would have a 1/6 probability. A non-3 on the second, 5/6. There are 5 non-6s that are on a die. For scenario number 2, getting a non-3 on the first roll would be 5 out of 6. Getting a 3 on the second roll would be 1 out of 6. Notice each of those individually, we needed one thing and another to both happen. But consider these two scenarios. You can't have scenario 1 and scenario 2 both happen at the same time. So we'd have to find them separately and add them. We'd have scenario 1 or scenario number 2 happening. We've got to cover our bases and make sure we consider the different ways that this could play out. And now we got some cleaning up to do. 1/6 times 5/6, 536. Same with the other set of parentheses. Add them up. 10 over 36 reduces to 5/18. It's always a good feeling, right, when you have an answer that there is in the answer choices. We had the decision to make about and versus or. This problem happened to have both of them, happened to have and with each individual scenario, and then the or when we said, well, I can't have scenario 1 and scenario 2 both happen. It's got to be one or the other. So I mentioned earlier that when there are multiple events, and so if you missed it, like Jane Austen says in Love and Friendship, and one's plight is one's opportunity. one of the decisions that you've got to make when you have multiple events going on is and versus or. But there's another decision that, as a savvy GMAT test taker, that you're going to have to make. The other decision is, are we talking about dependent versus independent events? Independent probability is where what happens in one event has no impact on what's going to happen on the next. Like rolling one die has no impact on the composition of the die of what's going to happen the second time. Same thing with coin flips. But then there are other occasions known as dependent probability, where what happens in one event is going to have an impact on the next. Imagine you have 10 poker chips. 4 of them are red, 6 of them are black, placed into a bag. We put up the visual here on the right side. 2 are selected at random, one after the other, without replacement. What is the probability that both are black? Now, both are black means we want a black the first time and a black the second time. So we're going to find their probabilities separately and multiply them, of course. The first time you go to that bag, you desire a black poker chip. There are 6 of them out of a total of 10 chips. I realize that reduces to 3/5. I want to leave that for a minute as 6 over 10, because consider what's going to happen next. That phrase, without replacement, is absolutely crucial, should make your antennae go up. Because what that means is that we're going to remove that black chip and we're not going to put it back. We have altered the composition of what is in that bag for when we go back the second time. We go back to the bag the second time, and again, we desire a black chip. But this time, there's not 6 of them left. We had taken one away. And the total number of chips isn't 10 anymore. We had taken one away. So that means for the second chip to be black, our probability is 5 over 9. What happened in the first pull from the bag affected the composition the second time. This is called dependent, or sometimes called conditional probability. Oh, but we do want the first and the second to be a black. So the first and the second, we find them separately and multiply. 6/10 times 5/9. So we can do some reducing certainly here. Either at the end, 30 over 90 is 3/9 or 1/3. Could have reduced earlier in the process, certainly too, if you wanted to. When we had here the probability that both are black, if you're thinking, but wait a second, Gene, what if it wasn't selecting black at first? What if it was red at first? Well, here's what you've got to remember. Probability of any kind is always desired out of the total. So if at any point you pick a red chip, well, that's not counted in desired anyway. And if you get red, black, or black, red, or red, red, none of that. Those would all have a 0 probability of what is desired. So multiple events. You've got 2 decisions that you've got to make, and versus or, independent versus dependent probability. Keep that in mind. Try out this next problem, try it on for size, and see how it fits. Put your answer down in the comments below, and then we'll review. I think we're starting to get some consensus in the comments. Ravish, 215th, Daniel. We have, yeah, a lot of C's coming up. 215th, Deeksha, sold. Yeah, 215ths it is. And of course, more importantly, let's talk about how we get there. We don't want you to care just about this problem after all, but rather, underlying methodologies, thought processes that you'll be replicating in your practice with probability questions in your march towards the exam. A bag contains only 6 red discs and 4 blue discs. 2 discs are drawn consecutively at random without replacing the first. We want the probability that both discs are going to be blue. The first time you go to that bag, you desire a blue disc, 4 of those, out of a total of 10 discs, 4/10, without replacing the first. So we're going to take a blue disc out. We're not putting it back. So when we go back to the bag the second time, the composition of the bag has been altered. This is dependent probability. Now you've got, out of all of those discs, you've only got 3 that are blue left out of a total of 9, 3/9. We want the probability that both discs will be blue. The problem didn't use the word and, but that both discs, this is not a word find, right? You're getting ready to go to business school after all, but we do want a blue and then another blue. So we find those probabilities separately and multiply. 4/10 reduces down to 2/5. 3/9 reduces then down to 1/3, multiplying along the top and along the bottom of those. Answer choice C. That indeed is the right one. Now let's give you another one here to practice with, where maybe it's not, how shall I say, maybe not as direct as this problem was with indicating what exactly will be desired. This next problem, sweet. In fact, talking about something sweet, talking about jelly beans. So sometimes you have to do a little kind of decoding of what is it that's actually desired in my various events. But again, having to make the decision, dependent versus independent probability, and versus or. Try this one on for size. See how it fits. Put your answer in the comments below, and then we're going to review. Oh, getting some disagreement down in the comments. A few B's there. Navid and Beatrice got a D there from Anubhav, 1/455. Got an A there from Dragosh. Got some more B's up here coming up. The disagreement. This is why we talk about these. This is why we hold events like this about demystifying probability. If you got a little stuck on it, that's okay. It's why we talk about these things. And of course, I've got to say, I really admire Susan's willpower in this problem, that Susan's got a whole jar of jelly beans and Susan can resist the urge to eat all of them on the first day. If it were me, I'd probably just eat all of them on the first day. But Susan resists the urge, and Susan eats one jelly bean every morning. Now we start out with 15 cherry and 3 banana. At the end of 3 days, what we want is for there to be only cherry beans left in the jar. Now consider what this means would have to happen on every one of those original 3 days. There are 3 banana jelly beans to start with, right? So after 3 days to have only cherry, what must have happened in each of the 3 days for Susan? For there to be only cherry, Susan would have to have eaten banana, banana, banana on each of those 3 days. That's the only way to get what we desire, which would be only cherry beans left in the jar. So what this problem really is just a fancy pants way for the GMAT to ask you, what is the probability of getting banana, banana, banana on those 3 days? Hey, Gene, why didn't they just say it that way? But it's where, where's the fun in that? Test makers want you to get a high score, but they want you to earn it then in the process. Susan goes to the jar the first time. We want her to eat a banana jelly bean. 3 of those out of a total of 18 jelly beans, but she doesn't put it back, right? She eats the jelly bean, would be pretty hard to put it back afterwards. So then the second day, we only have 2 banana jelly beans left out of 17. Remember, 1 jelly bean had been removed. Susan's going to eat that banana jelly bean, then come back the next day. Only 1 banana jelly bean left out of a total then of 16. And so we do have there, looks like Abhishek, right? Giving us the math very beautifully here, right? 3 18s times 2 17s times 1 16. Now, of course, the quant section of the GMAT, you don't get to use a calculator. Integrated reasoning, different story. So instead of multiplying along the top and along the bottom and then reducing, look for opportunities to reduce early. Like 3 over 18 reduces to 1/6. 2 and 16 reduces down to 1 over 8. So we have 1 over 6 times 17 times 8. And if you didn't feel like multiplying out those numbers, and frankly, I don't blame you, what you could do is use the answer choices to your advantage then. Consider what the last digit will be for 6 times 17 times 8. 6 times 7 is 42, ends in a 2. Times 8 is 16. We need something that ends in a 6. B and E are the only games in town. And if you consider that 6 times 8 is 48 times 17, it's going to be way bigger than 216. Well, so then it's got to be left. That then is answer choice B. Yeah, see some B's come up here. Oh, see, Navid asking about the difficulty level of this question. Hold on, I think I actually happen to have it. What is this, number 4? About a 650. About a 650 level problem. And I think the main reason that it would be that as opposed to, let's say, like in the low 600s is because we have that kind of decoding to do early on. But you've also, whether it's a 750 level problem or a 450 level problem, when you're dealing with multiple events, you still have to make those decisions, of and versus or, and dependent versus independent. Looks like Shubham asking, is this type of question common to the GMAT? That's a very good question. And so the answer is, it depends on the score level at which you are getting questions. So here's the thing. It is an adaptive test, right? It's a great question we have there from Shubham. I hope I'm saying your name correctly. I apologize if I'm not. When you have an adaptive test, right? The better that you're doing, the more questions you get right, the harder and harder the questions start to get. So when you're getting like, 500, 550 level problems, you're not going to see something like this. You'll get like very simple probability, maybe just slightly easier than that bullseye problem earlier. But as your score goes up, and as you start seeing harder questions, that's when the GMAT starts throwing in these little twists and turns, having to decide about and versus or, dependent versus independent. Some problems have both and or, like we saw earlier with rolling a 3 on those dice. And another twist, like you saw here, is that we have to decode only cherry means banana, banana, banana. So as far as a question like this in front of you, common on the GMAT, in the higher scoring levels, like the harder questions you're getting, the more little twists, more little variations the GMAT might throw in. I hope that helps answer your question, Shubham. So since we had so much fun here with Susan, let's take Susan with her jelly beans again and have you do a data sufficiency problem. Because if you're wondering, hey, Gene, we're like, what, half an hour into this event, we haven't even done a data sufficiency problem with that. This is an outrage. Don't worry, we won't let the injustice stand. The reason that we haven't had you do one yet is not because I want to somehow deny you the joy that I know you experience from doing data sufficiency problems. But probability way more often comes up in word problems with problem solving, but it does come up in data sufficiency from time to time too. I'm going to turn off my camera and mic, give you a chance to do this one up, but like with any data sufficiency problem, try and get away with as little actual math as you can get away with. Little logic, little critical thinking really goes a long way. Have a good time with it, and then we'll review. Before we talk about the analysis here for this one, Caleb asked a good question. I guess it's kind of related to Shubham's question too. How many probability questions can we expect to see in the quant section? So let me give a two-part answer to that, because it's a great question we have from Caleb. One is the higher you're scoring, the more of them you are likely to see. So if you're getting like 500, 520 level problems, maybe you'll see one, maybe two. Once you get to like, 600, 650 level problems, now you start seeing maybe like 3 or 4, maybe 5 per section. Once you're in the neighborhood ballpark of 700 above, you're probably going to see 1 or 2 more than that. But here's the other part to that. And this is, Caleb, that, we can't give you a definite number, but the GMAT has pools of questions that they pull from, right? And at the different difficulty levels, the pools will have a different composition. We could probably do a probability question just with that. So if you're seeing, let's say, 700 level problems, their pool of 700 level problems is going to have lots more probability questions in that pool than like a pool of 500 level problems. Now, does that guarantee that the questions that will be pulled from that pool will end up being probability questions? No, but certainly the odds start to go up. So I would say you're going to see, at the very least, you're going to see a couple of them. But the higher and higher your score goes, basically, the more and more you should care about probability. I wish I could give you a much more definite answer to that, Caleb. But it's basically about the, what are your odds of seeing them? Your odds of seeing more of them goes up as your score level goes up. This one indeed is a data sufficiency question, right, David? That's why we didn't put down those answers. Well, that's why we didn't put down the answer choices, because for data sufficiency, you just want to memorize what each one represents. What you can call A, B, C, D, E, or we at Kaplan often call the 1, 2, TN, kind of the shorthand. So we've got to set our standard for sufficiency here. Looks like we have what do we have? A number of B's coming up, got a C in there too. I'll keep you in suspense. Let's find out what the right answer is. I'm kind of curious myself, I must say. Jar with only cherry and banana jelly beans. This time, unlike the previous problem with Susan, where the GMAT was nice enough to tell us how many of each there were, this time the GMAT has the audacity, the unmitigated gall to not tell us how many we start with. Every morning for 3 days, she selects and eats a cherry jelly bean. So 3 jelly beans have been eaten. 4th day, selects a jelly bean at random and eats it. What we want is the probability that on the 4th day will be cherry. Well, it would be nice if we knew that by the 4th day, how many cherry are left out of the total number of jelly beans, desired out of total. That's our standard for sufficiency. If a statement gives us that, it will be sufficient. If not, it will be insufficient. Statement one wouldn't give us the actual numbers. Statement number one just tells us we have the same number of cherry and jelly beans in the jar to start with. Remember, they said the jar contains only cherry and banana jelly beans. So with statement one, you could even pick numbers, consider how could this go. 1/2 in the jar of banana. So the other half would be cherry. What if it was 5 cherry and 5 banana on the first day? Then 3 cherry get eaten. 4th day, you now have 2 cherry left out of 7 jelly beans, a 2/7 probability. But it didn't have to start out with 5 and 5, could have been 4 and 4, for example. And then if Susan ate 3 cherry, she'd have 1 cherry left out of the 5 jelly bean, different probability. So statement number one, not sufficient. And we can cross out some answers at that point, can cross out the 1st and 4th answer, what we call a Kaplan 1 by itself and each. Statement number 2, however, gives us something a little bit more specific than what statement number 1 gave. We actually know the concrete number of jelly beans on the first day. That means after 3 get eaten, we would know the concrete number of banana and of cherry jelly beans on the last day. Now, if at that moment you recognize that statement number 2 is sufficient, bonus. You just say, hey, statement number 2 is sufficient. Yeah, that's the final answer. And then you move on with your life, right? You don't have to do any work. But if you don't spot it right away, you don't throw up your hands and say, well, I give up. You can consider how this could play out or how it would play out. 9 banana, 9 cherry on the first day. She eats 3 cherry. And then that means by the time the 4th day rolls around, there's 6 cherry left out of 15. We do have the definite numbers for desired outcomes out of the total number of outcomes. Statement number 2, sufficient. No need to combine the statements. Statement number 2, already sufficient by itself. Now, Abhian asks, does this question ask us to find whether probability of selecting cherry is higher than the probability of selecting a banana? No, they could have phrased it that way. They could have, instead of it being, so this is a value data sufficiency question. What's the probability the jelly bean Susan selects on the 4th day is a cherry jelly bean? That's a value data sufficiency question. They could have given us the same setup, and they could have asked us a yes-no question, what you're referring to, Abhian, something like, is the probability of eating a cherry on the 4th day greater than the probability of selecting a banana then on the 4th day? So it could have asked us that. It's not what it did ask us here, though. If ever you are working here on, what level question would this be considered? From Ken and Apollo, what is this one, number 5? This one also about the mid-600s, about a 660 level question. We're going to be doing, by the way, at the very end, the last couple of problems, we're going to be looking at 700 and above level questions that we do. So we're kind of building up to that in this lesson. If you're ever working a probability question and you're not even sure how to exactly start, well, you could start by just laying out the formula and dealing with the pieces separately. For example, here, what's the probability of tossing exactly 3 heads in 4 flips of a fair coin? And those, of course, would be, unlike what we saw with Susan, these would be independent events. What happens in 1 flip of a fair coin has no effect on what's going to happen on the next flip of the coin. We can find the total number of outcomes by saying, well, every time you flip a coin, you get 2 outcomes. So 2 on the first, and on the second, and on the third, and on the 4th. Well, every time you find yourself saying the word and in a probability question, that means multiply. 16 total outcomes. Now, how to find exactly 3 heads out of those? Some students want to use the combination formula. And they say, oh, I know, I'll use the combination formula. I'll make N4, I'll make K3, I'll go. Check yourself before you wreck yourself. Much of the time, the numbers in probability questions are going to be small enough. A little careful counting really goes a long way. To get 3 heads, well, that means the one remaining toss would have to be tails. How can this shake out? Well, either the one tail would be 4th or 3rd or 2nd or 1st. I'm not even advocating necessarily that you write out the H's and T's if this were the day of your exam. You certainly could, but you could even count on your fingers, right? The one tail could be 1st, 2nd, 3rd, or 4th. That would be 4 desired outcomes out of the 16 total, that's 4 over 16, or then 0.25. So I wanted to bring up this problem as sort of a segue into what we're going to look at next. We're going to look at a couple other little twists and turns, and we're going to certainly leave a little time for additional Q&A at the very end. But I want to use this one as sort of a segue, because if you're ever stuck on how to even begin a probability question, you could just start by laying down the formula and then dealing with the pieces separately. This can come in especially handy for higher difficulty problems. And I know I could tell from the questions below that a lot of you are interested in the various difficulty levels. Well, this one next up here, this would be like around a 730 level problem. And there are a few little twists and turns. Now, I want to walk you through this one to bring up a pretty important part of the inner monologue of the GMAT champion, and then have you do a similar one afterwards, right after. A fair coin is tossed 5 times. What's the probability it lands heads up at least twice? We can lay down the formula, desired outcomes out of total outcomes. Even if you can only find one of those pieces, see what you can eliminate. Let's say it was question 31. Let's say in the quant section of your exam, if you're running out of time and you had to make a strategic guess, at least you want to try and make it a strategic guess. Total outcomes. You toss the coin the first time and the second and the third and the fourth and the fifth. Every time you find yourself saying "and" in a probability question means multiply. We get our total number of outcomes here then. But this is not 2 times 5. This is 2 times itself 5 times. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. 32 total outcomes. Well, what's an answer that we can already eliminate right now? 32 might reduce down to 16, but there is no way that 32 is going to reduce to 5. I mean, 5 isn't even a factor of 32. So that means that we can at least eliminate answer choice C, even if we don't do anything else. Now let's work on what's desired. We want the probability that the coin is going to land heads up at least twice. Now, this covers a lot of ground. That could be 2 heads with 3 tails, 3 heads with 2 tails, 4 heads with 1 tail, or 5 heads with 0 tail. I mean, that's a lot to keep track of. So maybe we shouldn't keep track of that. Maybe instead, we should determine what's non-desired. Let me share with you a little GMAT secret. I wasn't sure if I wanted to share GMAT secrets with you all today, but what the heck? You seem like nice people. Why not? When you see language like at least, or at most, or no less than, or no greater than in a probability question, that's typically the signal that there's going to be less work for you to do, less daylight between you and the GMAT points to figure out what's non-desired, and then afterwards then subtract from the total. Well, if we desire heads landing up at least twice, what's non-desired? Getting 0 heads with 5 tails, or getting 1 head with 4 tails, a lot less to keep track of. So now let's find what's non-desired and then subtract from the total number of outcomes. How can we get 0 heads with 5 tails? Some students want to use the combination formula. You check yourself before you wreck yourself. Little careful counting can go a long way. How can we get 0 heads with 5 tails? There's only one way that can happen: getting tail, 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 tail for every coin toss. One way. How about getting 1 head with 4 tails? Well, think about how many different positions there are, for lack of a better word, for where our 1 head could land. Our 1 head could land first, or second, or third, or fourth, or fifth. Notice I'm saying or, right? Because it can't have all of those that are going to happen. 1 head has 5 different positions it could land. So all in, we have a total of 6 non-desired outcomes. There were 32 total outcomes. If 6 of those are non-desired, well, that leaves us with 26 desired outcomes. Up top for desired, I'm going to put in 26. Now, they do make your work for this one, but it would take way, way longer to figure out all the desired things there on the left, rather than finding what's non-desired and then subtracting from the total. You might feel like you're done with the problem, but the problem's not done with you. You still have to reduce that fraction. 13 over 16 is then answer choice D. Now, imagine for a moment this had been one of the last questions of your GMAT, right? It's a high difficulty problem. If you're running out of time and had to make a strategic guess, here I think would be a good way to play it. If you anticipate what the GMAT is trying to reward, those who notice the phrase at least or at most, and know, oh, okay, I'm better off finding out what's non-desired and then subtract from the total, you got to bet the test makers know that many students are going to get so wee-weed up in the math, it's a technical term, they'll forget to do the last step. In other words, it's likely that there will be the right answer, of course, that represents desired probability, and then some trap answer, some wrong answer that would be non-desired. Well, remember something from the very beginning of this hour, that the sum of probability is for all the mutually exclusive outcomes for a certain event is 1. Notice the only 2 answers here that do add up to 1 are B and D. You can narrow it down to those 2, 50-50 shot. Not so bad, right? If you consider that logic at the beginning. And if you have a few extra moments, you can say, there's just a lot more stuff that's desired. I'm going to lean towards then answer choice D. Wouldn't be 100% bulletproof if it is a strategic guess, but it would certainly improve your odds, improve your probability then. So it ends up being right, Apollo, ends up being D. So before I turn you loose on doing the next problem on your own, and then we'll do a little Q&A then right after that. The headline here, right, the takeaway, in probability questions that use language like at least or at most or no fewer than or no more than, that's typically going to be the signal that the best approach is going to be to figure out what's non-desired and then subtract from the total outcomes or the total probability, which would be 1. Keep this in mind. I'm going to give you a couple minutes here to try this one on for size. This one also, this one about a 720 level problem. Again, it's because of that little twist similar to what we saw in the previous one. So take things piece by piece, which I think is good advice for solving word problems anyway. Hang in there. Eye of the tiger, dare to be great, and then we're going to review. Put your answer in the comments if you want to when you've got it. I'm starting to see quite a few D's coming up here. Apollo, David, Shanawaz, quite a few D. That's D for doggone it. That is indeed the right answer. Now, more importantly, I want to emphasize here before we talk about the analysis here for this problem, I wouldn't expect you, I don't think it would be reasonable for anybody to expect you after this session to immediately feel like a total pro with probability. I can go take the GMAT tomorrow. Doesn't work that way, unfortunately, but kind of built into our learning objectives for this session is to kind of plant the seeds, right? Arm you with the important principles and guidelines that will make your practice a lot more effective. So let's get down to brass tacks. You've got the student in a computer science class building Building a circuit with transistors. Box has 10 transistors, 2 of them defective. Select 2 at random from the box. What's the probability at least one of them is defective? Now think about the different things that could happen. When you select 2 transistors from the box, you could have neither defective, just the first, just the second, or both are defective. Now what's desired? That at least one of them is defective. So that would be those last 3 things. If we were going to directly go and calculate that, it'll take some time, right? We have to deal with them separately and then combine them afterwards. That language, at least, that's the signal that there'll be less work to do to figure out what's non-desired, that neither is defective, and then subtract from 1. Remember, probability, sum of the probabilities for all mutually exclusive outcomes for a certain event is 1. Well, how do we get neither to be defective? Well, that would mean the first transistor you pick is not defective. There's 8 of those out of 10. The other one you pick, and here, dependent probability, you can't pick the same transistor twice. The second one then, out of the 9 transistors left, 7 of them then would be non-defective. We multiply those together, can reduce the fraction certainly. 8 over 10 is 4 over 5. And we have 28 over 45. That is a trap answer here. That is answer choice E, because then we have one more step to do. That would be what's non-desired, subtract from 1, 17 over 45. That then is desired. And other phrases that would include, Caleb, similar to at least, that would indicate that that's the strategy to take to figure out what's non-desired and then subtract then from the total would be at least, at most, no more than, no fewer than. But just generally speaking, if you visualize, is there more stuff to keep track of with what's desired or more stuff to keep track of for what's non-desired? I mean, just generally then, if you give a few moments of thought to that, then at the very beginning, generally then you could say, all right, well, will my better course of attack, and I use that proactive verb deliberately, or I want you to take control of the exam, would my better course of attack be to deal with what's desired or what's non-desired and then subtract from the total? Oh, while we're looking at this problem, if you were running out of time and you had to make a strategic guess, just like in the previous problem, notice there are 2 answers here that add up to 1, D and E. Chances are one of them's desired, the other one's not. And so you can narrow it down to those 2, and you can consider then, well, most of these transistors aren't defective, right? 8 out of the 10 aren't defective. So you lean towards the smaller one of those 2 then. Would it be 100% bulletproof? No, but pretty good odds, pretty good probability if you did have to make a strategic guess. Now, before we open things up for some extra Q&A then at the very end, here are I think the big takeaways that we want you to take away from this session. Probability, regular standard formula, desired out of total outcomes. When you have various events going on, you have to decide whether it's and versus or. If you want one thing and another to happen, you find their probability separately and multiply. If you want one thing or another to happen, you find their probability separately and add. The other decision is independent versus dependent probability. Independent, like coin flips or rolls of dice, one event has no impact on the next, but dependent probability, like selecting jelly beans one at a time or poker chips and not putting them back, we saw earlier, one event does have an impact on the probability of the next. And then relating also to Caleb's question, language like at least, at most, no more than, no less than, no fewer than, would typically be the signal that probably the best course of action will be to determine what's not desired and then subtract then from the total. Total outcomes, if you want to think of it that way, or total probability then would be 1. So thank you all for your hard work. We're certainly going to open things up here for some Q&A. So if you have some Q's, I'll try and include some A's, certainly too, if you want to put some in the comments below. And certainly this video is going to be available to you. So, we at Kaplan and the folks at GMAT Club are going to be monitoring the comments, right, in the coming days and beyond. So if any then questions or comments pop up, you put them in as you review this video in the coming days, see if any questions or comments pop up, and then one of us will be happy to answer them. If you are leaving, though, first of all, certainly stay safe. Right? It's a good time to stay home and build some GMAT skills. And you want to make sure to give this topic the attention it deserves. And I hope you feel a little bit better about probability and having a plan of attack than when we first started this hour. So if any questions or concerns come up, now would be a good time. Let's see what we got coming up here. When again are we going live? So that might be a question. I think the next Kaplan event in the partnership with GMAT Club isn't going to be for, I don't think we even have an exact date on that yet. So I'll leave that question to our friends at GMAT Club for when the next GMAT Club event is going to be doing live. What other probability formulas, Kima asks? And so, by the way, Deeksha, so same thing, I'll leave that to our friends at GMAT Club that'll post about that, about when the next event is going to be and when the next topic is going to be. Oh, and in the meantime, too, check out Kaplan has a bunch of free resources if you want to check out. If you go to captest.com, Kaplan has a bunch of, classes, of course, but also free resources, got a practice test, got a question of the day, 20-minute GMAT workout. I always like to say you get the score you earn through taking advantage of all the various GMAT resources that exist out there, getting your hands on as many problems as you can, and kind of hammering away at it till it becomes really comfortable and natural. What learning scientists call the 3 R's, recall and repetition, would be the keys to retention. Let's see what else we have. Oh, glad you enjoyed it, Dragosh. Let's see, Ravish, thanks a lot for, well, we're glad you joined us, Ravish. Onwards and upwards, GMAT soldiers. Vivacious. I've been called a lot of things, Amreen, but I will happily take vivacious. Great work in here, Beatrice. Great work in here, Annika. Ken asks, how many probability questions can we expect to run into? This kind of, I think, relates back to, I believe it was Caleb asked something similar earlier. So I can't give you an exact number for that, Ken, because it is an adaptive test. So if, basically the higher your, the more questions you get right, the harder and harder the questions start to get. As you start being served up harder questions, the probability of you seeing more probability questions starts to go up dramatically. So when you're being served up like 500, 550 level questions, you might only see like 1 or 2. Once you get like into the 600s, knocking on the door of the 700, you're going to likely see more, 4, 5, maybe even more of them. But, it's not like an exact concrete number. I don't want to give you a concrete number if, there isn't a set number. In, let's say, the pool of 700 level questions, a lot more of them are going to be probability. So when the GMAT pulls a problem from the pool of 700 level questions, your odds of getting a probability one are going to be much higher than if the GMAT is selecting a pool of from a pool of 500 level questions. So I guess my answer would be the higher your score goals are, the more you should care about probability, because the higher your score goals are, the more probability questions you're likely to see as your score moves up. And that's when you see some little, variations, like we saw a few here in this hour. Hope that helps, Ken. Gia asks, can we do a permutation and combinations session next? I hope so. I'll leave that to our friends at GMAT Club. I think that's a topic that lots of people like, permutations and combinations, whether order matters or whether order doesn't matter. Other questions, comments, concerns, observations, objections, GMAT anecdotes, or a GMAT sonnet, perhaps? I'm glad you found it well presented and helpful. Glad you enjoyed it, Ken. Thank you for joining us. Ravish, when we face higher level questions on probability, it is sometimes mixed with other topics like sets, right, and combinations, although not as many as you might think. So like with a couple of a couple of problems that we saw in this session, weren't there a couple of cases where you heard me say, well, for this part, a lot of students think, oh, I know I got to use the combinations formula for this part, when in fact, a lot of times when students feel like they've got to use that formula, a lot of times it's more trouble than it's worth, where a little careful counting can really go a long way. So yeah, I mean, Kaplan certainly has a lot of resources that tackle those combined topics. And I hope we get to do another event. I'll leave that to our friends at GMAT Club that deals with combinations and permutations. I'm sure that would combine some probability too. But the thing is, a lot of times when you feel like a probability question also requires the combinations formula, not all the time, right? Let's be honest. Sometimes you will have to use the combination formula within the solving of the problem, but most of the time you actually won't. That you'll just have to carefully count. I mean, take the one with getting 1 heads out of 4 tosses, right? No need to use the combination formula there. Just count. Heads could be first, second, third, fourth, or fifth. I always like to say the cardinal sin of GMAT Quant is always over solving. Yeah, of course, Apollo. Of course, that's what I said, right? And it's the times that we live in right now, I think is especially a good time to I mean, here we get to this cool thing about living in the internet age. We get to we meet here from all over the world, and we get to practice some GMAT skills and do some social distancing, certainly in the process too. But I think it's also a good time to take advantage of the time to stay home and do more GMAT problems, of course. Probability with circular arrangements in the future, from Gurjeet says. Yeah, I hope we can do another probability lesson and talk about some circular arrangements. I mean, the hour that we did here called Probability Made Easy is a very good start to develop like the bedrock for your success with probability questions in GMAT Quant. And then as you kind of gain more familiarity and start to feel the instincts like kick in, like, becomes almost like robotic and mechanical as you start to feel this stuff in your bones. I'm a former Kaplan GMAT student. I wasn't born learning this stuff. And so, it takes a little bit of time to really start to develop almost an instinct for what to do in certain probability questions. But then, even with the circular probability, a lot of times what happens there, like certain probability questions, and I hope we can do another one that gets into even more little variations like that, Gurjeet. But a lot of times with those problems with circular arrangements, even then the same kind of principles apply. Like, all right, let's say you have one person sitting in one spot, and let's say there's 4 other people, and maybe it'll be like older person, younger person being arranged or something like that. So you can find out how many arrangements there are and find out how many desired outcomes there are. So a lot of the same principles are going to apply. Thank you, Vashpal. Let's see. Does Kaplan have GMAT ratio videos for practice for viewing on YouTube? Caleb asks. Do a YouTube search. Very, very possible. I don't remember off the top of my head, but you do a YouTube search, type in Kaplan GMAT ratio, see what comes up. Best way to prepare for the GMAT, practice as much as you can. Yeah, well, of course, right, Annika, you practice as much as you can, but it's not about just like trying to churn through like the volume of problems. It's also about pattern recognition is such a big part of that preparation, where you don't want to. Nice thing about it being I don't want to get too philosophical about this, but nice thing about it being a standardized test is it is a predictable pattern-based test. The same kinds of questions show up repeatedly, same kinds of strategies get rewarded repeatedly, the same kinds of mistakes get penalized repeatedly. So yes, it is getting your hands on as many practice problems, as many practice tests as you possibly can, but also recognizing certain patterns as you do that. Like, oh, I see this problem with the defective transistors. Let me think back to other problems where I saw probability with at least in it. What was my game plan there? All right, so I'll apply the same game plan here, so that by the time you sit for the actual exam, it's not a matter of, hey, I've never seen anything like this before. So as a Kaplan GMAT teacher, I would almost want to tell students, yes, you do a lot of problems, but it's in the review of them that really a lot of the really good learning takes place, where you get to know the inner guts, the inner workings of a lot of these problems, to reinforce what you're doing right and maybe identify some things you're not doing right, so then you could repair them. So I'd almost tell students like, yeah, get your hands on as many practice problems as you can, but I'd rather almost see you do fewer problems, but make sure that you the problem itself should fade in your memory, but make sure that you get some good concepts and patterns taken from them, rather than just doing question after question after question after question, and like treating each one like it's some kind of anomaly, like it's some kind of independent entity. I'm sorry if I gave you a long answer to what seemed like a short question, Annika, but I'd rather be too thorough than not thorough enough. Vishpal, do I need to register a Kaplan to access free tests? You have to give your email address, because then they send you the info via email, but you don't have to be an enrolled Kaplan student to access a free test. We'd love for you to be an enrolled Kaplan student, of course. I'd love to see you in class. I hope you don't mind very bad math jokes. I use a lot of those in class. But to register for one of the free tests at Kaplan, it's not like you have to be a registered student, but you do have to enter your info, your email address, right? Because then they send you a confirmation and all of that. Oh, glad you enjoyed it, Ravish. Glad you enjoyed it. We always find that those students who kind of enjoy matching wits with the test makers and don't dread their GMAT practice, right? And that's, I mean, obviously all of you here are serious about doing well on this exam, why you're joining us here on a lovely Friday for this work. It's always the students that kind of enjoy matching wits with the test makers that it bodes very, very well for their ultimate success. The twin pillars of your ultimate success, maybe not even in the GMAT, but even beyond, effort and attitude, right? Putting in the effort, always with the attitude of, all right, here's something I could do a little differently, and I'm not going to beat myself up over doing something wrong. But it's always the student who can say, all right, here's something I could do a little differently next time to have that improve. I mean, that's the student I think all of us really bet on when test day comes. See you next time, Caleb. Bye, Annika. Great working here. All right, so I guess we'll close up shop. The video, of course, will be available to you. If any questions or comments pop up at any time, you can put them down in the comments. One of us from Kaplan or for GMAT Club are going to be monitoring it and going to be answering those questions, of course. And do I teach at any other platform or university other than Kaplan? Nope. Kaplan keeps me pretty busy, Vashpal. So they keep me pretty busy these days. Although the platform, just various online platforms that Kaplan uses, and when we go live with certain events on YouTube and Facebook. But no, Kaplan keeps me pretty busy. Well, yeah, I hope so. Sarayu. I hope so. So these session that we're doing now is GMAT Club invited Kaplan, right, to do this event, and I was honored that Kaplan asked me to do this session here on probability. So as far as can we do more combinations, permutations, more geometry, stuff like that, I hope so. Hope our friends at GMAT Club that we can work together and make more of these sessions. All right, so I guess we'll close up shop. Remember, if any questions or concerns pop up at any time, you can put them in the comments. One of the folks either at GMAT Club or one of us from Kaplan are going to be monitoring it. In the meantime, please stay safe and happy GMATting. Onwards and upwards, GMAT soldiers.